Well, hello everyone. I am Priya from UC Irvine, and I hope you are doing great in the age of COVID-19. Also, the past couple of months it shows that there are many things that are much more important than knowledge graph. But today I'm going to talk about revisiting evaluation of knowledge-based completion models. This is joined for by me, Yifan Pian, and my advisor, Professor Samir Singh. I'm going to start my talk by giving a brief introduction on knowledge graph completion. Then I'm going to share the shortcoming that we find for the current evaluation protocols. And finally, I'm going to provide the solution that we find for these shortcomings, which is introducing Yago 3TC benchmark. Let's start with knowledge graph completion overview. Knowledge graphs are representation of information in the form of a graph where nodes represent entities and edges represent the relation between entities. Knowledge graph usually created through several sources of information such as unstructured text, structured text, and images. Because of the way these knowledge graphs are being created, there are many missing information inside them, resulting in creation of knowledge graph completion task. Here, the goal is to identify missing information using all kinds of other information that we have in the graph. For example, knowing that Barack Obama is married to Michelle and further Barack has a daughter named Sasha, our goal is to being able to predict that Michelle has a daughter named Sasha as well. Further, since we don't know the non-existent links are true or false, we force to adopt ranking metrics as an evaluation measure. While in real-world application, mostly we want to know whether information is true or false, and we don't care about the ranking. More specifically, there are two fundamental approaches to evaluate these knowledge graph completion models. The first one is the ranking metrics, which try to rank the subject or object of the target triple in comparison to the pool of all possible entities, which again doesn't correspond to real-world use case in many instances. And further, triple classification, which try to classify each triple as true or false by learning a threshold for each relation using the validation data. By that, I think we are ready to move on to discuss about the actual shortcoming. But before diving into the details, I want to lay out the three negative sampling approaches that we consider in this work. The first one is random sampling, which is widely adopted, and replace the subject or object by a random entity from the pool of all possible entities. The second sampling that we consider is the constraint sampling, which first filter all the entities that at least appear once with the relation of target triple. Then we replace the subject or object with a random entity from this specific subset. Finally, we consider careful sampling, which first identify all the entities that never appear with the relation of target triple, and then replace the subject or object with the highest score entity using a knowledge graph completion model. In this presentation, I'm going to talk only about three issues that we find in the current evaluation approaches. I'm going to start with the calibration. We observe that calibration study is not well defined for these knowledge graph completion models. More specifically, in Yago 3 data for three models of Tucker, Rotati, and Dismals, which were state-of-the-art results at the time that we conduct this experiment, we see none of these plots are actually calibrated, and they are very under confidence. The red lines is the ideal model that we are looking for. We see similar performance for constraint sampling and as well careful sampling as well. And there are 2 points in this plot. Firstly, most of these plots are not calibrated at all. Secondly, we see as we make the negative sampling more challenging, the behavior of each model become completely different, and demonstrating that the ambiguous nature of calibration study for these knowledge graph completion models. The second issue that we observed was the existence of semi-inverse relations in knowledge graph. More specifically, we observed that in WordNet 18RR, there are 4 specific relations that whenever we see them in the training data with a high possibility, we see the same triple with the same component, but with the reverse relation as well. These relations consist 40% of training data and 30% of the test data, resulting in a very high performance of 0.9 MRR on these triples. Similarly, on Yago 3.10, we observed that whenever we see, in 80% of the time that we see a relation placed 4 between 2 entities, we see relation is affiliated to between those 2 entities as well. These relations consist around 55% of training data and 50% of test data, again resulting on very high MRR performance. The problem with these relations is the fact that since they are very simple to predict and they appear a lot in the knowledge graph, they result in ranking metric not being able to reflect reasoning power properly. Finally, I'm going to talk about the triple classification robustness. Here we see the accuracy of this classifier on 3 base WordNet, and Yago tree, we observed that when we train this classifier using conventional way, but change the negative sampling in the inference time, the accuracy dropped dramatically, demonstrating that these classifiers are very brittle. I just want to point out that the current trivial classification results is around, is naively around 90% as we see in this class. Now the question that remains is how we can resolve this issue. We are looking for benchmarks that aligns with real world application goals, and further can properly differentiate between these knowledge graph completion models, and finally can capture reasoning powers of these models. And the challenge that we are facing to come up with such benchmarks is basically the fact that knowledge graphs are not complete. There are many, many non-existent leaks in them, and identifying any labels for each fact is very hard and expensive. The solution that we came up with for all of these challenges issue was Yago tree TC benchmark, which we created by firstly select a random subset from Yago tree test data. Then we identified top scoring triple from for each one of these target triple using a knowledge graph completion models. And then we filtered these triples using several rules guaranteing the factuality of each one of them. And finally, we get the labels for remaining triple using our crowdsourcing pipeline. In our crowdsourcing pipeline, after identifying top scoring triple for each target fact, we pass them through our first round of crowdsourcing with 3 participants. If just one of them think a triple is positive, we pass that specific triple through a second round of annotation with 2 participants. This time, if both of the annotators agree that the triple is positive, we accept the label. Going through our crowdsourcing pipeline, we could gather around 30,000 triples, from which around 10% of them has positive label. Now let's see the evaluation result on Yago tree TC benchmark. We first consider triple classification. In this experiment, we consider another baseline named as type C, where as our classifier, we simply check whether the subject and object of target triple match with the relation type using training data. As we can see in the figure, these simple baselines perform very similarly to a state-of-the-art result models, casting doubt on the whole progress that we have so far on the knowledge graph completion models. In the paper, we try to come up with several measures to improve the performance of these models, but we are far from the acceptable performance. We further see a huge drop in accuracy in this plot comparing to the previous result that we have, which was around 90%, which we believe is capturing reasoning power of these models more realistically. We further conduct experiment on calibration. As we can see in this figure, there is 2 points here. Firstly, we see the order of models is reverse here, having the Tucker as the most calibrated model right now. And further, we observe that now all of the models are overconfident compared to previous results that were underconfident, which consistent with the previous calibration study on neural network models. Through this talk, we first observed that ranking metrics are not very trustworthy. We further noticed that triple classification is not robust, and these evaluation metrics do not align with real-world application goal, resulting in creation of Yago tree TC benchmark as the first step toward better evaluating these knowledge graph completion models. As a final note, I just want to mention that we intend to create a web-hosted evaluation platform to continuously update Yago tree TC using new knowledge graph completion models. In this talk, I had a chance to go through all of these topics, and you can see the website for our project and my contact information here. Thank you for your time.